Let's investigate how image intensity varies along the line that I've shown here in red. And in particular, let's focus on what happens here at the tail of the P. And if we look at the intensity profile here, and these pixel values, these grayscale values are double precision values that vary between 0 for black and 1 for white. And we see that it starts off with a low value around 0.2, where we're on the black paint, the background of the sign. They rise up to a value of around 0.8 when we cross the white paint, which is the tail of the P, and then fall off again to low background values back onto the black paint. We might be interested in looking at the horizontal gradient, and we can approximate the gradient as the difference between a pixel and its neighbor on the left-hand side. Simple numerical approximation to the gradient. However, this is not a very symmetrical way to think about this, so instead we can represent it this way. The intensity in the horizontal direction of pixel U is the difference between its neighbor on the right-hand side and its neighbor on the left-hand side, and divided by 2. This would represent the horizontal gradient. Now, the gradient expressed in this form we can write as a kernel. It is a small kernel represented by a 1/3 matrix. If we apply this kernel to the input image, the result will be an output image whose pixels comprise the horizontal gradient at the corresponding point. Here is an animation similar to ones that we've seen before. In red, we see the input window marching across the image from left to right and from top to bottom. As it's moving, we are computing the output values and dropping them into the output image. Note again that we're not computing the left-hand edge and the right-hand edge of the output image, because this is where the input window falls off the input image. We can see the gradient being computed. We can see areas of gentle horizontal gradient, we can see areas of much stronger horizontal gradient where we have that discontinuity, and we can see areas where the gradient is negative. Let's apply this to the image that we were looking at earlier, and we can do that quite simply using the toolbox function iconv. We pass in the first argument, which is the kernel, and the second argument, which is the image. What we can see here is that the left-hand edges of the letters are coded blue. That means that they have positive gradient. That's where the intensity is changing from the dark of the background to the white of the letters. On the right-hand side of the letters, where the intensity falls from white down to the dark background, it's got a negative value, and this is shown as red. So what this kernel is doing is highlighting vertical lines within the scene, because vertical lines have got a strong horizontal gradient. I denote this image as I subscript U. This is a common way to denote image gradients. The subscript represents the direction in which the gradient is being computed. Now we can do a very similar thing by rotating the kernel, and now we can compute the gradient in the vertical direction. So the kernel now is the transpose of the kernel we used to compute horizontal gradient. It will allow us to compute vertical gradient. We can apply that to our penguin sign. This is what the kernel looks like, and this is what the output looks like. It's got some similarities to what we saw before. As we move down in a column, we see that the tops of letters are blue. This indicates that they have got a strong positive gradient. Remember that in an image, the vertical coordinate increases downwards. So at the top of a letter, we're moving from the dark background onto the white paint, and so we have a strong positive gradient. On the bottom of the letters, there's a strong negative gradient as we fall off the white paint and down onto the black background. So the vertical gradient image has highlighted the horizontal lines within the image. We can compute this in MATLAB using almost the same function as before, except we have transposed the kernel. The kernel is a 1/3 matrix, and we use MATLAB's transpose operator, the quote symbol, in order to transpose that kernel into a 3/1 matrix. A very common kernel used in image processing is called the Seibel kernel, and it has some similarities to the simple kernel that we used before. I like to think of this kernel as computing the horizontal gradient on the current line and averaging that with the horizontal gradient on the line above and on the line below. We can obtain the value of this kernel using the toolbox function kSeibel. If I apply this function to our penguin image, I can obtain a horizontal gradient image, as is shown here, which looks quite similar to the horizontal gradient we just looked at. The function I sub L, we pass it an image, and it returns both a horizontal gradient image and a vertical gradient image. A really important feature in an image, a very common feature in images of man-made scenes, are what we call edges. So what I'm going to do is to load an image that we've seen before. I'm going to display that. And here is the sign about penguins again. And what I'm going to do is to look at an intensity profile along a roughly horizontal line from here to there. And what we see is the intensity has got a low value to start with, and then as we cross each of the pieces of white paint on the sign, we see that the intensity goes up. Now let's zoom in a little bit on that. It's a little bit too busy. I'm going to expand this region here, which is the beginning of the word look. And what we see quite clearly here is that the pixels have got quite a low value, less than 0.2. Just the background of the dark background of the sign moves up to around 0.6, 0.7. The white paint as we cross the letter L, and then down again to a value of 0.2. And then pixel values increase as we cross the remaining letters. But what we can see is that as we move from the dark to the light, the intensity increases quite rapidly, and then it falls quite rapidly on the other side of the character. So we're going to explore this idea of gradient, or the rate of change of grey level as we move horizontally across the sign. Often in image processing, we're interested in areas of the image where there is a lot of gradient. We don't care whether it's horizontal or vertical. We don't care whether it's positive or negative. We just want to know where there's a lot of gradient. And this is computed quite simply by computing the square root of the sum of the squares of the horizontal and vertical gradients, and it results in an image like this. Most of it's black because there isn't much gradient over the background, but where there is a lot of gradient around the edges of letters, this function has got a very high value. So this is a great operator for highlighting the edges of objects within a scene. And we can obtain an image like this using the function I sub L with no output arguments. We might also be interested in the direction of maximum gradient. In this image, pixels are increasing by a value of 10 every pixel in the horizontal direction, and by 5 every pixel vertically. So the direction of maximum gradient change is in this direction, 26 degrees with respect to horizontal. Now we can apply that same technique to the sub L image that we computed before. We can compute a gradient image, and that's the arctangent of the vertical gradient image element-wise divided by the horizontal gradient image. It looks a little bit too busy, so let's zoom in on the letter P. And if we look at the gradient direction on the left-hand edge of the P, we see that it has got a gradient direction value of 0. It's coded as white. So if we look at the color bar over here, we can see the 0 corresponds to 0 radian angle. And we expect this. On this side of the letter, the gradient is increasing in the horizontal direction from left to right. On the other side of the letter, the gradient is in fact increasing from right to left, because it's at this point that we're falling from the high white value down to the dark value. So the gradient is right to left. And we can see on this side of the letter, the gradient angles are either plus pi, which is shown as dark blue, or negative pi, which is shown as dark red.